Hi, my name is Dasha. I'm doing my PhD at the University of Twente at Power Electronics and EMC Group. I'm also a part of the STEM project, and today I'm going to present a couple of printed circuit boards that are representing a commonly met electromagnetic phenomena, and we're going to start with the self-induction board. So a self-induction board consists of two SMB connectors, a wide ground plane underneath the PCB, and a flexible and shielded wire on the top of the PCB. And together with the ground plane, which acts as the return path for the current, the wire creates a loop. And by changing the position of the wire, we can manipulate the area of the loop. And this will affect our transfer properties of the board that we're going to check in this demo. So we are going to start with a frequency domain, and for that we are going to measure S21, and I'm going to connect my VNA to a board. And we're going to measure in the frequency ranges from 1 megahertz to 1 gigahertz. And S21 is a transmission coefficient or a ratio between the output voltage to the input voltage, or in other words, is how much of the signal that we send from the port 1 have returned to a port 2 through the board. So first of all, we are going to measure S21, so a transfer properties of a big loop, and I'm going to hold the wire as far as possible from the ground plane. I'm going to do a sweep, and on the screen, the red line that we see, the red trace, is a 0 dB trace just as a reference. And in blue now we can see S21 of a big loop, and I'm going to save this trace, and it's going to become green, and I'm going to do a sweep of a small loop. I'm going to place the wire on top of the PCB as close as possible to the PCB itself, and this is going to minimize the loop. I'm going to sweep again, and we're going to see if there is any difference. Signal transfer is limited at high frequencies, but in case of a big loop, the signal is attenuated to a greater extent, and this is happening because of the self-induction, and self-induction depends on the area of the loop. And self-induction is a process in which a current is created that will oppose the change in the magnetic field. So we have a changing current in the conductor that will cause a change in the magnetic field, and this changing magnetic field will induce the current in the nearby conductors or in the active conductor itself. And a current is going to be created that will try to oppose the change in the magnetic field. And we also know this from the impedance formula, that the impedance of the inductor is going to increase with frequency. And this is what we see on the screen right now. Basically, it's a low-pass filter or a wire that acts as a low-pass filter, but the low-pass filter that we didn't want to create. So the same effect of the high-frequency signal being attenuated because of the self-induction we can observe in time domain by supplying the board with a square voltage. So here I have a generator, two-channel generator. Both of the channels are generating the identical signal. It's a square wave with the amplitude of 1 volt. And one of the channels is connected to the oscilloscope, and this is a yellow trace. And the other channel of the generator I'm going to connect to the input of the board, and the output of the board I'm going to connect to the oscilloscope. And the output of the board we're going to see as a magenta trace. So you can see that when I press the wire to as close to the PCB as possible, the slope of the magenta trace is almost identical to the yellow trace, to the initial signal. And if I lift the wire as far from ground plane as possible, creating a large loop, then the slope of the magenta trace becomes slower, and this means that the high frequency components are attenuated by the self-inductance. So we just saw an effect of long loose wire mounted on top of PCB, and you're probably thinking it's not very practical implementation. So I want to show another board which is more practical, and this is actually what you can see in real life and also implement in your PCB design. So this is a Lenz Law board, which is a more practical application of a self-induction board and the Lenz Law. And we have an input connector on the top of the PCB and multiple connectors on the downside of the PCB, and they're connected to the input by different traces with different characteristics, like geometrical characteristics. But the most important thing is that the ground plane is placed on the edges of the PCB, and this ground plane is shared for all of the traces that are on the PCB. So first I'm going to connect the PCB to the VNA again, and I'm going to connect the output 1 to the VNA, which makes the active track to be track 1, which is a white short trace and not on top of the PCB. So the signal goes here and returns still through the ground plane here, and it creates the biggest loop here on the PCB. I'm going to perform a sweep. And save this trace so it will become green. And then I'm going to connect my output to the output 1. And this will make the active trace to be a trace 7, which is a thick trace on top of the on top of the ground plane, with guardian traces on the sides. And it makes the small loop together with the return path because the track is placed on the top of the ground plane. And I'm going to make a sweep again. So as we expected, the trace that is placed not right on the ground plane, but creates a big loop together with the ground plane with the return path, causes higher losses at high frequencies, even though it looks physically like a shorter path for the current. And on the other hand, the very long trace, actually the longest trace on the PCB, but the one that is placed right on top of the ground plane, creates very small loop, and that's why it causes less losses in the transfer of the signal. Apart from that, a bigger loop will also mean that we create a bigger flux around the circuit, and that will mean that our circuit will be able to better couple to the other circuitry around, and also will be more susceptible to the interference of others. So it is very important to keep the loops as small as possible.